So we have an example here about the superposition of the magnetic field created by wires. Just looking at the picture, I see a vertical wire with a current of 5.6 amps and a horizontal one as well. The vertical one goes up while the horizontal one goes to the right. And I see some points P and Q, which are nice and symmetrically spaced away from the wire. Usually that means that it cuts down on the amount of math that we're doing, and instead we're focusing on the physics of what's going on here. So let's get to reading here. Calculate the direction and magnitudes of the magnetic fields at points P and Q. Consider carefully the contribution from both currents to the field. So every current is a moving charge, and moving charges create magnetic fields. And so both currents, both wires, are going to create a magnetic field, which is going to have some value at P and Q. Okay, and the distances there are just telling us what the distances to those points are. The way that the magnetic field is created is in this right-hand rule number 2 sort of way, where you could put your thumb in the direction of the current or the moving charge, and your fingers will curl around it in the direction of the magnetic field. Okay, and so uh, make this fist sort of thumbs up motion, and try and imagine that your thumb, the green one is the current. Any wire you run your thumb along it, it's going to create a magnetic field if there's a charge flowing through it. We can quantify that charge using the equation down here. B equals mu naught I over 2 pi r, or 2 pi s. R is just the distance, the sort of perpendicular distance from the wire. So if I had a point, let me draw one here in green. If I had a point right here that I was interested in, R is just this distance, direct distance to the wire. But sometimes you'll see books use S as a distance there. Now, mu naught is actually just a constant, 4 pi times 10 to the minus 7, or it's like 1.256 times 10 to the minus 6 Tesla meters per amps. It's just a constant of proportionality. It doesn't really mean much, I think, to you, except that it tells you how much magnetic field does a current generate. It's related to that value. Yeah, and so here, these pictures, these are telling you the right-hand rule sort of way that the magnetic field is generated. And in a side view, uh, you can imagine that if you turn your thumb to the side, so your thumb is that way, your fingers are sort of curling around. Well, now your fingers are pointing directly towards you at the top, but if you imagine curling them around, they'll point away from you at the bottom. And so we have an out of the page B field here, and an into the page B field there. And actually this side view picture is identical to our horizontal current. So let's get back to it. And here we've got this horizontal current providing a magnetic field, which is going to, in the same way, wrap around in this way. And put your thumb in the direction of the green arrow, and the blue arrow is going to be the magnetic field generated. If you imagine your thumb down here in green, your magnetic field generated at point P is going to be, well, put your hand with your thumb to the right, and your fingers are going to be pointing towards you at point P. Okay? If you wrap your fingers around and keep going, they're going to go, and now they're going to be pointing away from you. Might have to twist your hand. Be careful not to hurt yourself. They're going to be away from you at point Q. Okay? And let's do a little bit more standard notation here. Into the page is an X and a circle, and out of the page here is a dot and a circle. And so this horizontal current is going to generate an out of the page field at point P and an into the page field at point Q. The vertical one, and we'll do this one in red, if you put your thumb, upwards, you can see that it's going to generate an out of the field, out of the page field at point P. It's going to wrap around and form a big circle. But if you slide your hand down to where point Q is, it's actually going to be the same. It's still going to generate an out of the page field at point P, and go and wrap around sort of this way. And so let me erase some of the markings just to make it a little bit easier to see, and only keep the standard markings. That blue is the horizontal blue is going to generate a field out of the page at point P, and so is the vertical one. But at point Q, blue is going to generate an into the page, whereas the vertical one is still going to generate an out of the page field. Superposition says we can sort of think of these independently and add them together as a vector. It's kind of hard to do that as a vector, but we can, since they're sort of directly towards or directly away from each other, we can think of this as being the magnitudes, just the magnitudes. And so considering point P, both of these are in the same direction. Blue and red are in the same direction, and they're going to come together to form a full magnetic field at point P, which is going to be equal to whatever the magnetic field at point P from the, I'll write H for horizontal, plus the magnetic field at point P from the vertical. Okay? And for each of these, so they're going to follow that same equation, mu naught I over 2 pi r. Same equation, mu naught I over 2 pi r. In theory, these could be different. Let me write a little h just to make that clear. In theory, these could be different, h at point P. Oops, sorry, that was actually the vertical, so this should be the horizontal, just to keep my color scheme intact. So red is vertical. In theory, these are different, but in this problem, they are actually the same, because these distances from blue to P is, as we said here, 0.5 meters. But that's the same as the distance from the red vertical one, to point P as well. And also the current, the red current is 5.6 and the blue current is 5.6 as well. That's nice. That just means we have to do a lot less calculator work, but it doesn't really change the physics of the scenario. If you want to plug either of these in, right, they're the same, so let's just do the blue one. 4 pi times 10 to the minus 7 Tesla meters per amps is your mu naught value. The current, the blue current is 5.6 amps. And on the denominator, we have 2 pi. The distance is half a meter, 0.5 meters. And if you plug everything in here, well, actually, before we do that, let's double check our units. So I have meters on top, meters on bottom, and these amps get canceled out. I do end up with Teslas, which is what I'm expecting this magnetic field to be. But I got 2.24 times 10 to the minus 6 Teslas. Minus 6, oops, Teslas. As being the magnetic field from the horizontal. The vertical one, you could do it if you want, but it's the same numbers. It's going to be the same, and so therefore the BP is actually going to be twice that, 2 times this 2.24, and so it's going to be about 4.4. 8 times 10 to the minus 6 Teslas. For reference, the magnetic field of the Earth is 5 times 10 to the minus 5. So even a 5.6 amp, which is fairly large, half a meter away, doesn't really generate that strong of a magnetic field. If you get closer, though, that will be much stronger. Now, how do we contend with point Q, it's even easier because the red and the blue are in opposite directions. Then B at Q, we have to subtract them. They're in opposite directions, and these are vectors. We got to respect the vector direction. So BPH minus B at P due to the vertical, V. And since they're the same numbers, they just happen to be, then this is going to be equal to 0. 0 Teslas. The two magnetic fields cancel out, and that's what can happen with superposition. This problem would have been more annoying with numbers that aren't the same, because then we would have to do this process, potentially 4 times. But hopefully this helps you understand how we're supposed to superimpose the fields due to multiple wires.